L'orateur aujourd'hui, c'est Satya Majumdar qui va nous parler de matrice aléatoire, de l'équation KPZ des atomes froids. Donc, comme je le disais, Satya est quelqu'un qui est à la pointe vraiment de ces sujets actuellement. Déjà, il était à Orsay, au lieu de la théorie des matrices aléatoires. Donc, il a appris auprès des gens les meilleurs et il a développé beaucoup de résultats récemment. Et à mon avis, c'est une des personnes qui est vraiment les plus en pointe sur ces sujets. Donc, je suis très heureux qu'il ait pu venir parler aujourd'hui.
Merci. Donc, merci beaucoup Bernard pour l'introduction et aussi pour l'invitation. Pour moi, c'est la première fois ici au Collège de France et je suis très honoré. Donc, merci beaucoup. Et, donc, je vais parler, mais je vais donner mon séminaire en anglais malheureusement parce que, comme beaucoup de gens qui savaient que mon français scientifique, c'est pas terrible, je suis plus à l'aise en anglais, donc je suis désolé pour ça. Donc, j'espère que vous allez m'excuser pour ça. Donc, okay, so I switch to English now. So I'm going to talk about 3 different topics: random matrix theory, KPZ, and cold atoms. And so we have already heard quite a lot about KPZ from Bernard and also from last week's course of Team Halpin-Healy. So I'll spend very little time on KPZ and I'll more concentrate on the first part and the third part. So this is the 3 topics. So first I'll give a sort of brief introduction to random matrix theory, mostly from historical perspective, and also tell you what is this Tracy-Widom distribution. And then, as I said, I'll skip most of the KPZ part because this has been already well discussed here. And finally, I'll come to one topic which we are currently very much interested, which is a quantum mechanical problem, the problem of trapped fermions in a confining potential in one dimension. And so although these 3 problems look very different from each other, what I want to show you is that they are actually quite related to each other. And so that's the sort of main topic of my talk today. Okay, so let's start. I'll start with a sort of introduction to random matrix theory, and then I'll come to the other parts. Okay, so random matrix theory and the Tracy-Widom distribution. So what is random matrix theory? So historically, the first ever paper in random matrix theory appeared in this journal called Biometrica in 1928 by John Wishart, who was a statistician in Cambridge, actually in Edinburgh and then later in Cambridge. And so this is it is something called Wishart matrix in random matrix theory, and this is exactly the joint distribution of the eigenvalues of this matrix. I'll come to that later. Was exactly what Bernard had written down for the result of Johansson, and so you see they are all connected. So let me just tell you what Wishart was interested in, and so he was interested in the following very simple problem. That imagine that you have a class of students, let's say 3 students as an example, and you have, let's say 2 courses like physics and maths, and these are just the exam scores. Okay? So this is the score of note of the student 1, student 2, student 3 in physics, and this is in maths. Okay? In general, this will be some rectangular M cross N matrix. And so the question that Wishart was interested in is that, so you look at your empirical data, that is the scores, and then you ask, okay, looking at this, what can I say about the correlation between the physics and math scores? If somebody is very good in mathematics, is he or she necessarily good in physics or vice versa? Okay? So how would you actually analyze that? So for that, so obvious things to do is to take the transpose of this matrix and take the product X transpose X. So this is called W. So W is going to be a 2 by 2 matrix in this example, but in general it will be n by n. And if you look at the elements of this W matrix, just a product, so what you see in the diagonal, it's x11 square plus x21 square plus x31 square. Okay, so imagine that these are scores, but they are centralized so that the mean is 0. And if you divide by 1/3, which is the overall factor, So this is just the variance of the physics course of these 3 students. And similarly, this object is just the variance of the maths course in these 3 students. So diagonal elements are just the variance, and the off-diagonal element here, this is just the covariance between the physics and maths, the correlation between physics and maths course. Okay? So therefore, this matrix, it sort of gives us the sort of information about the correlation in general, fluctuations, which is present in this empirical data. And so by analyzing the eigenvalues and eigenvectors of this matrix, that we might be able to extract some information about the correlation present between the physics and maths course. However, if you want to do that, so you have to compare it to something. So I mean, for example, if you take this course to be completely random without no correlation at all, okay, just totally random Gaussian variables, let's say. So in that case, again, if you form this, so these will be random elements now, and so if you diagonalize, the eigenvalues and eigenvectors will have some structures, and so the question is, I mean, but you can use that as a null model, because when you have your empirical class, you get your data and you have to compare it with something, and so you want to compare something where there is no correlation. Okay, so this is a completely random data. Okay, and then you just construct the covariance matrix and ask what is the eigenvalue and eigenvalue structure of this completely random matrix. So, and you can use that as a null model to compare your empirical data. Okay, so this is how this is the birth of random matrix. So as a null model in statistics and of the random covariance matrix, and this is the sort of work of Wishart, and he didn't really calculate the joint distribution of the eigenvalues of this completely random covariance matrix, but that was done later. And so this is the sort of starting of random matrix theory, and then in physics, I mean, it's Wigner who actually introduced random matrix theory to analyze the data in nuclear physics. And in fact, I mean, it's funny that Wigner, actually most physicists think that Wigner who thought of random matrix, but in fact he says here, then as I mentioned, this was known a long time ago by Wishart. This was a conference, and there was a discussion at the end of the conference, and somebody asks him that where does one find about the Wishart distribution? And so Wigner replies that Wishart distribution is given in S.S. Wilkes' book about statistics, and he found it just by accident. So accidents happen, and accidents can be very good sometimes. And so what was the idea of Wigner? So let me just state it very briefly. So imagine that you have like some heavy atoms like uranium-238 or thorium-232. So experimentalists can give you the energy spectrum of this. So these are the energy eigenvalues of these complicated nuclei, and similarly these are the energy eigenvalues of this nuclei. And you want to know that so what do you want to, what do you have to do in order to get such a spectrum? So in principle, what you have to solve is, so let's say this is your nuclei, and you have certain number of protons and neutrons, and you want to solve, say, a complicated Schrodinger equation, and the eigenvalues of the Schrodinger equation will give you the energy spectrum. But the problem is that you often don't know what the Hamiltonian itself is, because it's very complicated Hamiltonian. You don't know what is the structure, what is these things. And so how are you going to analyze these things? So one thing you notice that even though the details of where the spectrum, where the eigenvalues are, differ from uranium to thorium, but there is something similar between these two pictures, which is there's some kind of self-similarity. Okay? So indeed, what Wigner asked the experimentalists to do is to plot the spacing distribution, the nearest neighbor spacing distribution. So you look at the spacing between two neighboring eigenvalues, and you plot that this distribution of the eigenvalue. So of course you have to rescale it. So if you plot this P of S versus S, where S is the spacing between nearest eigenvalues, And if you rescale, that is, S is in the units of the mean spacing. Mean spacing will be different from uranium to thorium, but once you, express your S in the unit of the mean spacing, then the chances are that, for maybe thorium you get this, and for uranium you'll get a curve like that, and they fall exactly on top of each other. In fact, this was the picture which was there, sorry. Yeah, so this was the picture that you see here, the spacing distribution. And so this is the first universality, that what you see is that, once you have, rescaled by the mean spacing, it really doesn't matter whether they're almost identical, okay, they fall on the same curve. And so the question was then, if I want to really reproduce this curve, it's not, imaginable that I have to solve this complicated Schrodinger equation, because the Schrodinger equation, Hamiltonian of this problem will be different from this problem. How can I possibly get the same curve? Okay. So in fact, Wigner's solution to that was that, well, maybe if it is so complicated, this is a wrong starting point. What we should do instead is, think of the Hamiltonian. So Hamiltonian in some basis, it will be a matrix, n by n matrix, if you have n protons or neutrons, and you look at the eigenvalues of this matrix, but assuming that the matrix is completely random, okay, because you don't know what the detailed structure of these things. When a system is very complex, maybe the first approximation you can do is to assume that the elements are completely random, except that of course they have to satisfy some basic symmetry, which is, for example, in this case it will be Hermitian matrix, and then if you do that, then maybe chances are that it might actually give you a very good answer. And in fact, this was the case. If you just assume completely random matrix, and in fact then just look at the spacing distribution, and it turns out that it describes the nuclear data very well. And so this is the sort of start of the random matrix theory in the physics literature. And then it was, of course, followed by many other people, amongst them Dyson, Goda, Mehta, and many things were developed here in Saclay, and beautiful techniques of random matrix theory. And so, but the main idea of Wigner was precisely that if a problem is very complicated, somehow it becomes simpler. So in the sense that if you have a complicated problem, but it has some matrix representation in something, then you can just close your eyes, and first approximation you can try is just a random matrix and see what it gives. And if you're lucky, that you might actually get very good answer. Okay, so that was the Wigner's dogma. And somehow this dogma of, this doctrine of Wigner, it was extremely successful in not just in nuclear physics. It started with nuclear physics, but in quantum chaos, disorder localization, gauge theory, matrix models, string theory, and growth models, interface directed polymers that you just heard from Bernard Stock, and also in cold atoms. And in mathematics, there's number theory, Riemann zeta function, and then integrable systems and many other things. You can see whole list. You can find a good reference of the sort of more modern applications of random matrix theory in this book, which is edited by Garno Takeman, Jinho Baik, and Philippe Di Francisco. So, but basic idea is always the same. That when some system with complicated interactions is very complicated, the first thing to try is to you may not be, it may not be right always, but sometimes you may be lucky, and it can give you a very good answer. Okay, so that is why RMT was extremely successful in all these problems as a sort of zeroth order approximation. Okay, so let me just start with a very basic definition. So imagine that I have a matrix. So you can think of this as your Hamiltonian or something, and so it's an n by n matrix. And so what I want is a matrix with real eigenvalues. So how can I get real eigenvalues? So you can, for example, we all know that if you take a real symmetric matrix, its eigenvalues are real. If you take a complex Hermitian matrix, again the eigenvalues are real. And the third case is called the complex quaternionic matrix, which is a bit complicated. I won't go into the details. And there also you get real eigenvalues. So these three ways are called the Dyson's threefold ways. Okay? So they are guaranteed to give you real eigenvalues. So once you have this type of matrices where you know that you have real eigenvalues, and then you have to assign randomness to the entries of this matrix. Okay? So this is what is called the ensemble, how you assign the probability distribution of the entries of this random matrix. So the simplest one is to assume that the Gaussian distribution. So for example, if I take a real symmetric matrix, so I have independent variables which is upper triangular block, because these are just by symmetry is the same as this one. And you can choose them each independently from a Gaussian distribution. So the joint distribution of the entries of the matrix is just exponential minus, let's say, Jij mod square with some variance sigma square. Okay? And so this is the simplest example. And this example, you see that because of this weight, particular weight, and you have chosen the variance in such a way that you can actually write this as exponential minus trace of J dagger J. J dagger means just the Hermitian conjugate. And once you have written this, then you immediately see that if I now make a rotation, that means if I make a change of basis, for example, if it's a real symmetric matrix, I can make an orthogonal rotation. And under this orthogonal rotation, the trace of J dagger J is invariant under the rotation. Similarly, if I have a complex Hermitian, if I make a unitary rotation, this is invariant under the rotation. And this is the principle that dictates this choice, because if it is a real, for example, system like a nucleus, I mean your Hamiltonian, your energy levels should be invariant under a rotation. Whichever basis you choose, it should have the same eigenvalues. And therefore, this is these are called rotationally invariant ensembles. So the name for this is GOE, is a Gaussian orthogonal ensemble, because it's invariant under orthogonal rotation. And similarly, GUE for complex Hermitian, when it's invariant under unitary rotation. And finally, this guy here, which is invariant under a Gaussian symplectic rotation. Okay? So these are the three famous Gaussian ensembles, and there have been a lot of discussion about other ensembles also, which I'll not go into the details. But once you give me this joint distribution of the entries, and then for each realization of the entry, I can diagonalize this matrix and I can get n real eigenvalues. And we'll see in a minute that these eigenvalues are very strongly correlated. Okay? So this is the n real eigenvalues. And so the spectral statistics of random matrix theory, the name of the game in random matrix theory is to understand the statistics of these eigenvalues. Okay? At least within this simple Gaussian orthogonal ensemble. That's the basic things. And so we want to know, given this, so if I change now my, my entries, another realization of the matrix, I'll get another set of eigenvalues. So they are random variables. And how do they fluctuate from one sample to another sample? What can we say about the general statistics of the eigenvalues? Okay, so this is the main problem. And so the first progress is to actually, okay, I wrote it here, Wigner, but I don't know really who was the first to derive this. But because Wishart didn't do it, but I don't know. It's a little bit, history is a little bit blurred here. But you can ask, what is the joint distribution of these n eigenvalues? Okay, given that the entries are independent Gaussian variables. So this is not a sort of trivial derivation. It's a little bit complicated. So, but I won't go into the details. I'll just tell you the main result. So this is a normalization constant, and here you have this exponential minus 1/2 sigma square summation lambda I square, which was basically there, before, because the trace of J dagger J, if you write in terms of eigenvalues, it just becomes this summation lambda I square. So that factor is there. But there's an additional factor, which is called the Van der Monde factor, which is lambda J minus lambda K to the power beta, as Bernard mentioned. And this is the sort of important part, because this actually gives you the correlation. And this beta here actually takes three possible values depending on whether it's a real symmetric or complex Hermitian or complex quaternionic matrix, beta equal to 1, 2, and 4. This is called the Tyson index. Now, where does this term come from? So mathematically, if you look at the derivation, so what are you going to, how are you going to calculate the joint distribution of the eigenvalues? Because, to do this, what you do is, because if you try to do it naively, it will be very complicated. So the idea is that, okay, you have your entries, which are your basic degrees of freedom. And first you want to make a change of variables. You go from the entries to eigenvalues and eigenvectors. Okay, so your entries are, let's say, this x11, x12. So for example, for real symmetric matrix, you had n into n plus 1 by 2 number of degrees of freedom. And from this, you make a change of variable, and you go to the change of variables are these n eigenvalues and the rest of the elements, which I call it Sij, which are the elements of the eigenvectors. Okay, I'm not going to the details, but if you look at the eigenvector, then there are some constraints that they are orthogonal, but there are some independent elements, and those elements and the number of eigenvalues n, in fact it turns out these are exactly n into n minus 1 over 2 elements, and here is n. So when you add them, you get n into n plus 1 over 2. So this is a sort of suitable change of variables, degrees of freedom, and so you make this change of variable, and then so you can write down the joint distribution as a function of these new variables, and then you have to integrate over the eigenvector degrees of freedom to get the joint distribution of the eigenvalues only, marginal distribution of the eigenvalues. Now when you make this change of variable, there is a Jacobian factor, and this is the origin of this term here is precisely this Jacobian in making this change of transformation. And this is what makes the eigenvalues correlated. Because you see, if you didn't have this term here, they will be totally independent, the eigenvalues, okay? And there will be Gaussian variables, eigenvalues are totally independent. In fact, this is exactly what is called the random energy model of Bernard, and it has been very useful in disordered systems for decades. And but here the eigenvalues are correlated because of this extra van der Monde factor which comes through the Jacobian. And later I'll show you some physics reason how it appears. Okay, so one thing you can do immediately, so once you have this joint distribution, then you can, you can always write x to the power beta as e to the power beta log x. So I can put everything inside the exponential, and I choose this, the variance to be 1 over beta n so that the eigenvalues are of order 1, and then I can just write down the whole thing as exponential minus beta by 2. So this is this term which comes here, and this term here using this trick here, so it just becomes logarithm of lambda j minus lambda k. Okay. So then I can think of this as lambda 1, the real eigenvalues on a real line as the positions of some charged particles. And these charged particles, so they have an energy associated with this particular configuration of charges. And this energy has two parts. So one part is a external potential, which is a confining harmonic potential, which is trying to push all the charges towards the center. And the other one is a mutual repulsion between these particles, which is trying to push them apart, okay, because they don't like to be next to each other. By the way, this is what is called the eigenvalue repulsion in nuclear physics, because it says that the probability that two eigenvalues are close to each other is going to be very, very small. Okay, and this is because of this repulsion term. So you can so now you can forget about your random matrix. You can think of this as a one-dimensional statistical mechanical gas in equilibrium with a Boltzmann distribution where this beta is like an effective inverse temperature, and the energy of this gas has these two parts. There is a attractive potential, overall potential, which is trying to push the gas towards the origin, and there is a mutual repulsion which is trying to push them apart. Okay. So as a result, what we would expect is that if this term was not there, everybody will be sitting at the center. And so what this term does is to push them a little bit apart because they don't like to be too close to each other. So what we would expect that on an average, the system will settle down. If I've taken the large n limit, the system will settle down in a finite region around the origin. And that's what happens when you and to first observable that you can actually measure, which is just the average density of eigenvalues. So this is normalized to 1. So this means that this is the fraction of eigenvalues between lambda and lambda plus d lambda. That's so you can formally write down as sum over delta function lambda minus lambda I, and the expectation value is over this joint distribution. Okay. Now this one I'm not showing you the computation, but this one what you can show is in this large n limit, as I said, that it settles down, so it achieves what is called the famous Wigner semicircular form, which says that the eigenvalues more or less settle down on a finite region of space from minus root 2 to plus root 2, and the density actually vanishes as a square root at the two edges. So there is higher density here, so more eigenvalues near the center, and then they go down as you go towards the edge. Okay? So this is the famous Wigner semicircular law. So we can push this further without doing too much computation. So you can ask, obviously, so given that the density is non-uniform, so there is a higher number of particles near the bulk, near the center of the trap. And let's ask, what is the typical interparticle distance between these things near the bulk, and what is the typical interparticle distance near the edge? So this you can actually do just a hand waving calculation. So to compute in the bulk, what I'll do is I take this Wigner semicircular form in the large n limit, and I integrate. This is the fraction. So this is just a fraction of particles between, let's say, one particle and to the next distance L. So if I integrate, because it's a fraction and it's just one particle here, so it's 1 over n. So if you set to be 1 over n, and now you just substitute this this form here, do the integral, and you get L bulk is 1 over n. Okay? So this is a very simple calculation. It's just roughly because you are putting n particles in a finite region of space, so the typical distance should be of order 1 over n. But you can use the same Wigner density to estimate what is the edge, the typical distance of between particles near the edge of this semicircular law. And this is again, you just integrate your Wigner density from, let's say, √2 minus some distance L edge to √2, and set it to be order 1 over n, okay, because that's the typical distance. And you see that because of the square root singularity here, when you integrate, you get a 3 by 2, and when you invert, it gives you that L edge is typically n to the power minus 2/3. So you get this, these two length scales, which are very important in random matrix theory. So one is the bulk, which is the typical interparticle distance, and this is much larger than the distance at the edge, which is of order n to the power minus 2/3. So this n to the power minus 2/3 is sort of plays a very important role, as we'll see in a minute. And in fact, I mean, this is the large n form, but you can ask what happens at finite n. At finite n, you will find some oscillations here, and these were calculated by first by Bowick and Brezin and Forrester and other people, but I'll not go into the details. Okay. But the main thing to learn from this slide is that the typical length scale at the edge is of order n to the power minus 2/3. Okay. So this is the 90s, and so there's a lot of excitements in both, as Bernard mentioned, in statistical physics as well as in mathematics over the last 20 years, is on the behavior at the edge of this semicircular law. That is, if you look at there, in particular, if you look at the top eigenvalue, okay, for example, either the lambda max or lambda mean, because this is symmetric in this case, but let's say the lambda max. So in terms of the directed polymer, this will be the energy max or energy mean. So this is a similar sort of variable here. Okay. So this is the lambda max. So largest eigenvalue. So I take my matrix, I diagonalize, and I just take down the largest eigenvalue, and I repeat this experiment again and again, and I can draw a histogram. And the question is, what can I say about this histogram? Okay. So what you can say immediately is that lambda max on an average fluctuates around √2. Okay. So its mean value should be √2. Okay. So this is the analog of the mean value that Bernard wrote down here, that 2 times square root of xy for the longest increasing subsequence. It's exactly the same. This is the mean value. And then you can ask, okay, this guy, of course, is going to fluctuate from sample to sample. What is the typical scale of fluctuation? And we have seen that, immediately from the previous slide, that the typical scale of fluctuation is n to the power minus 2/3. So these two informations you know already. So therefore, you just have to know what is the distribution once you subtract this mean and divide by this edge. And this is what is called the Tracy-Widom distribution. So basically, if you plot this lambda max, so as I said, its mean value is √2, and it will fluctuate on a scale of order n to the power minus 2/3. So this is the fluctuation. And so therefore, you can write down lambda max as a random variable, its mean value, deterministic part, plus a fluctuating part, which is n to the power minus 2/3, that's an order of magnitude, and then times a random variable of order 1. Okay? So this is the behavior for large n, and the question was, what can you say about this distribution of this random variable? And what Tracy and Widom did is to actually compute the probability distribution of this chi of beta. It depends on this Dyson index beta, and so in general, this cumulative distribution of this lambda max, once you have subtracted of the mean and scaled the fluctuations. So this is a scaled cumulative distribution, and its probability density is just the derivative of this guy. Okay? So this is the object they calculated. Now just to see what you need to compute mathematically this quantity. So I want to calculate this cumulative distribution. What's the probability that lambda max is less than or equal to some w, let's say. Okay? This is the object I want. Now this is the same as probability that lambda 1, each of them is less than w, right? Because if largest eigenvalue is less than w, evidently that all the eigenvalues should be less than w. And what we know is the joint distribution of these eigenvalues, which is given by this, as I told you. So all I have to do is to plug in this joint distribution to compute this probability. So the main problem, basic problem is to compute this joint distribution of largest eigenvalue, I need to do a multiple integral. So I plug in this joint distribution, I do this integral from -infinity to w. That's the probability that each of them is less than w. Okay? So this is the so the main technical problem with all this Tracy-Widom distribution is to how to compute this. We are given this, so it's a well-defined problem. You have given this measure, and you just want to calculate an n-fold integral, and you want to know what is the large n behavior of that. And as we said, the large n behavior should be that there should be, it should be a scaling function of this scaled variable. And this is what Tracy-Widom did. So just to, I won't go into the details of how they did it, but just to tell you exactly, what comes in. So there is one basic concept which is important and which will keep appearing in the talk, which is the idea of Fredholm determinant. I just mentioned, just to remind you what it is. Okay, so imagine that you have a matrix, n by n matrix, n cross n. Let's say I denote by Kij. Okay. I and j goes from 1 to n. So this is a matrix which is given to me. And suppose I want to calculate the eigenvalues and eigenvectors of this matrix. So how do I calculate the eigenvalue? All of us know that, you just this is the eigenvalue equation, right? So you have a matrix K, and you have a vector here, which is this psi lambda 1, psi lambda n. Pardon? Pardon. Merci. Désolé. Okay, so this is just our usual these things that you operate this on the eigenvector and you get the eigenvalue into this. Okay, and then if I want to calculate, for example, the determinant of this identity matrix minus this matrix K, so this is just product of this 1 minus lambda I. So I calculate the eigenvalues and then I just take this product, and this is our usual that all of us know from basic linear algebra. Now imagine that now you, instead of a discrete space, you have a continuous space, and I look at some interval, let's say AB. So I call this A, which is this interval AB. And so the analog of this matrix now, so you can imagine this interval consisting of many discrete points with infinite number of discrete points. Okay? And just imagine solving exactly the same equation. So but now it will be continuous variable. So I'll have a function instead of a matrix which is k z z prime. And again, if I want to calculate the eigenvalues, so now it will be integral. So this is the exact analogy of that, equal to lambda times psi lambda of z. Okay. So, but now the interval is over this interval A to B, and you compute these eigenvalues, and then if I want to calculate the exact analog of this object here, so this will be I minus, okay, this is sometimes denoted as PA, K, P. I'll tell you what this means. So this thing just means, so this PA is a projection operator. So it just says that the Z and Z prime both belongs to this interval A. That's all. So otherwise it's exactly same object. Okay? This is just to remind you that the two coordinates, they both belong to this same interval. Okay? And so this object, therefore, roughly speaking, informally speaking, this is product of 1 over. But now we have infinite number of eigenvalues because this is an infinite dimensional matrix if you think of this. Okay. So this is the object, so this is the projection, and this is the object which is called the Fredholm determinant. So it's an operator in the continuous space, but it's exact analogy of so Fredholm determinant. Okay. So once you have that, so as I said, so this is just what I said here. So you have imagine that you have a function. So instead of matrix, now it's called kernel, and its arguments are on a continuous space, k, z, z prime. And again, as I said, sometimes literature people write this as PA times PA, which is just to show that, just to indicate that z and z prime both belong to this interval A. Okay, so it's just an indicator function. And then this is exactly what I said. This is just the infinite dimensional matrix, and then the Fredholm determinant is just the product of this infinite number of 1 minus lambda I. This is the again identity operator. Okay, so this is the definition of Fredholm determinant. Okay, so once you have that, so what happens? And here I'll focus only on beta equal to 2 because that's a sort of special case, which is very sort of there's a lot of simplification. This is the GUE, and so what happens? What you can show, and this was a result which was known even prior to Tracy and Widom. Actually, it goes back to Godin, that the probability that the scaled variable chi2 is less than or equal to x is actually a Fredholm determinant of a kernel k, and this kernel k is just simply the integral of Airy function. So Airy z plus u, Airy z prime plus u times du, integral from 0 to infinity. So this is a function, and so x here appears in this interval a here. Okay, so x to infinity. So remember that, so you have to look at the Fredholm determinant, but with the kernel operating on x to infinity, and you have to find out all the eigenvalues, and then you can compute this function in principle. So they were not able to compute this function f to x, and this is what was Tracy and Widom did. So they actually managed to compute these eigenvalues lambda i's in some sense, and obtain this product in a closed form. Okay, so in fact what they showed is that this function, you can write it as exponential minus x to infinity some other function q square, and this q satisfies a Pauli-2 equation with the proper boundary conditions, which goes like Airy function z goes to infinity. So this is a bit technical, but this is the object which, so basically it's a Fredholm determinant, and Tracy and Widom could get the precise behavior, analyze this Fredholm determinant exactly. Okay, and this is the sort of main point. But they also did for beta equal to 1 and 4, which doesn't have this simple analog like this. So this simple Fredholm determinant structure appears because it turns out that the GUE process is what is called the determinantal process, but I will not go into the details of that. But for the other cases, it's a little bit more difficult. It's not, but nevertheless, they were able to compute this f beta of x. Okay, so how do the curves look like? You have already seen that it doesn't show that asymmetry in this picture because it almost looks Gaussian, but as Bernard showed you already, that the tails are actually given by, so this is the probability density of the lambda max, and when x goes to minus infinity, it goes like mod x cube. When x goes to plus infinity, it goes like x to the power 3 over 2. Okay, so and it turned out that in subsequent years that the Tracy Widom was found not just in this originally random matrix problem, but it came, it sort of appeared in many different problems. So Bernard already mentioned directed polymer, random permutation. Then you have this growth models, KPZ equation, then sequence alignment problem, large and gauge theory, liquid crystal, spin glasses. I mean, lots of different problems which apparently have no connection to each other to start with, but then you slowly find some mapping between these problems, and you can somehow map it to random matrix theory. And what I want to talk about today is this trapped fermions, where again this Tracy Widom distribution appears. Okay. So, and it has been measured in various experiments. So this is the growing liquid crystal experiment of Takeuchi and Shano that Bernard had talked about probably in his first course, or maybe Team Halpin-Healy, I was not there. And then it was also measured in coupled fiber lasers and then superconductors and so on. And in fact, now, I mean, it's known that Tracy Widom appears in many different places, and these are sort of two popular science articles, if you are interested, which talks about the ubiquity of Tracy Widom distribution. Okay, so that's sort of my brief introduction to random matrix theory. It already took some time. So KPZ equation, what I'll do is, I mean, please don't look because I'm going to skip many things because it has been already said. So I'll just go straight to the main equation. So we have seen that this is the KPZ equation in 1 plus 1 dimension. So this is the liquid crystal experiment. So imagine that you have a liquid crystal has two phases, let's say, and one of them under experimental conditions, one of them is a stable phase, the other is a unstable phase. So in the beginning you start with a white background, which is unstable phase, and then you nucleate a little bit of the stable phase, and then as time grows, the stable phase grows, it invades over the unstable background. And then if you look at this cluster, it typically looks circular cluster. And so the radius, which I call the height here, and so the height is a function of the transverse coordinate x and the time coordinate t. So it's a 1 plus 1 dimensional field. And what you see is that the surface is very rough, and this surface roughness grows like t to the 1/3 that Bernard mentioned. And so in order to understand, to have an effective growth model in a hydrodynamic continuum limit that describes this t to the power 1/3 growth law. So that was the KPZ equation, famous KPZ equation. I will not go into the derivation as Bernard has already done it, and here it's a white noise. And so what was known? Basically the width of the height fluctuation here goes like t to the 1/3 as time goes to infinity. So this was already known in the 80s, and what happens is that that more recent results is to actually compute not just the second moment, but the full height distribution at a fixed point in space in this geometry, which is, and in fact this was done by several people, mathematicians as well as physicists. And in fact what they showed is that indeed the full height distribution, once you center and scale it properly, it actually converges to the Tracy-Widom distribution of GUE. GUE because it has a particular geometry which is called the droplet geometry, the circular geometry. So then in a long time limit, it approaches to the Tracy-Widom distribution of the Gaussian unitary ensemble. So this was one of the applications of Tracy-Widom distribution. And in fact, in these computations, it was not just at t goes to infinity, but they were able to compute the full distribution even for finite t in a formal way, which I'll mention. Okay, and that will be useful for us. Okay, so I won't go into the derivation of these results, but basically what this was done in these papers that I mentioned is that if you, for example, you take this droplet geometry, I just put a cross section like to denote the x, and I look at a particular point in x, and I look at the height variable at different time, and so this is a fluctuating random variable, and if you properly, this is a height, okay, under some you have to subtract of certain things, and then if you look at this is a random variable, so you look at and you define an s, which is this is like a Laplace transform. So this is like you put e to the power minus s to the power minus, and then take one more exponential, okay, and you compute this strange looking generating function. So this is average is over the distribution of h. So this object on the left hand side is some generating function, although strange looking. It's not quite Laplace transform because they are double exponentials, and if you compute that, what it was shown is that this is exactly a Fredholm determinant that I mentioned of a kernel, which I'll show you in a minute. Okay. So this is the Fredholm determinant of a kernel, and the kernel actually has this form, and the time appears here in the bottom here at finite time t. So this is the exact result for any time t, and so you see this time appears here. And this PS is the project, S here is S, and so this is the projection operator from S to infinity. Okay, so Z and Z prime, this PS means Z and Z prime both belong to S to infinity. So basically on the left hand side I have a generating function parameterized by S and T. On the right hand side also I have a function of S and T, but it's a complicated Fredholm determinant. Okay. And in particular what you see is that in the limit t goes to infinity, this kernel here reduces precisely to the airy kernel of the Gaussian unitary ensemble, and then this is just precisely the Fredholm determinant of this airy kernel, and therefore this is the Tracy-Widom distribution in the long time limit. Okay, right hand side, and the left hand side you can show that. So what happens in the left hand side at long time limit? I can take this t to the power 1/3 outside, and and just take the long time limit, and then it sort of becomes a theta function of s minus this, which is precisely the probability that this height plus t over 12, okay, don't bother about this t over 12, divided by t to the 1/3 is less than equal to s. So the left hand side converges to this cumulative distribution of the rescaled height, and the right hand side converges to the airy kernel of the random matrix distribution. And therefore, you come to the conclusion that the cumulative height distribution in the KPZ problem, the probability that this is equal to less than s, in the long time limit, it approaches to the Tracy-Widom GUE function. Okay? So this is the sort of main result of these mathematicians. And so just to summarize, therefore, the KPZ height, you can write there's a deterministic part which grows linearly with t, because the cluster size grows linearly with t, the speed basically. And then there's a fluctuation which is of order t to the 1/3 times a random variable of order 1, and this random variable has the Tracy-Widom distribution. Now it turns out I didn't talk about it here, I only talked about the GUE geometry, that is the curved geometry. So curved geometry corresponds to the GUE Tracy-Widom. Now it turns out you could also study what happens in the flat geometry, and then it corresponds to Tracy-Widom GOE, although why the different geometry corresponds to different symmetry classes of random matrix theory is not completely clear, at least to me. And but this is the sort of main summary of the development over the last few years. And so what we learned from here is that the KPZ height is therefore has the same as a Tracy-Widom distribution and same Fredholm determinant that appears. But this is at long time limit. But I told you that the mathematicians also have the result for finite time t. Okay, so the kernel looks slightly different. The kernel actually has a t dependence, sorry, here, as a factor 1 plus e to the power minus t 1/3. So only when you take the t going to infinity limit, it reduces to the usual airy kernel. Otherwise, you have a time dependent kernel here. But this is an exact solution for any time t. So mathematicians use different methods, and by mapping it to weakly asymmetric exclusion process, whereas physicists use the replica method and so on. And so I will not go into the details. Probably it will be discussed, and you have seen this curve before. This is the experimental results and the comparison of Takaichi and Sano. So you see that circular geometry, which is corresponds to GUE, and this is this curve, and this corresponds to the flat geometry, which is the GOE. Okay. So and then in 2016. The 30 years of KPZ equation was celebrated in the KITP, where a lot of these things were discussed, and so it was nice to see that. Okay, so now I come to the third part of my talk, which is the KPZ and the cold atoms, and this is something that we have been interested for quite some time now. And so these are my collaborators, David Dean, Pierre Ledusal, Alberto Rosso, and Gregory Chaire, and okay, there are some papers here. And so let me tell you, this is a completely different problem. This is a quantum problem, and we'll see the connection to both the random matrix theory and the KPZ at the end of the day. Okay, so as you know, cold atom system is is a beautiful experimental system because you can do a lot of things with it, and by the manipulation of this experimental system, you can study both the quantum and thermal fluctuations of a many-body interacting system, in particular at low temperature. And in fact, the interesting quantum many-body effects can be seen even in absence of interactions. I mean, this we know from our basic courses. For instance, if you have a bosons, then even without any direct interaction, the bosons can, they all can go to the zero ground state energy at low temperature. They can all collapse onto the ground state, all of them. And this is what is called the Bose-Einstein condensation. Whereas in fermions, again, without any direct interaction, even in the non-interacting limit, they are not really non-interacting because there is Pauli exclusion principle, which is by definition of fermions, which tells you that two fermions cannot be in the same state. Okay. So there is a very rich quantum many-body physics even in absence of interactions. So, and experimentally, you can actually tune the interactions by tuning phase-back resonance and other objects. I'm not an expert on these kind of things, but what I'm trying to say is that even the non-interacting limit can be very, very interesting in these systems. Okay, so what's the typical setting? So typical setting is that you usually create a laser trap by laser optical trap in which you trap these atoms, and typically this is a harmonic trap, but doesn't have to be harmonic all the time. And so your atoms are sitting in this trap, and I'll talk about from now on about fermions. So basically these traps limit them in a finite region. So these are quantum particles, quantum atoms, and they are confined, they get confined because of the trap in a finite region of space. So now, so what happens here is that this trap introduces an edge, because you see that, I mean, these atoms are confined here. Now if you are near the trap center, okay, if the atoms are here, then you don't see the curvature, right? Because you are at the center, the curvature is, happening later. So here they more or less behave like a transitional invariant system. They don't see the curvature of the potential, trapping potential. So if you are interested in this bulk physics here, you can describe them by the usual traditional many-body physics, okay? But the problem is here, because of the trapping potential, it's not uniform, and then at some point, it sort of becomes, the density vanishes. So there is a well-defined edges at the two ends. And you want to know, what can I say about the physics at the edge? So the traditional many-body theory is not going to work, so I have to find something else. And so what we have shown that there is an exact mapping between these quantum problems, and the random matrix theory of GUE, Gaussian unitary ensemble. And thanks to this mapping, we can actually study the edge properties sort of very cleanly, analytically, and which cannot be done by the usual condensed matter many-body physics of the bulk, okay? So traditional many-body theory. So to see this, but before that, let me show you a picture, just to show you that these days experiments can actually image the positions of the atoms. So this is a 2D fermions in a harmonic trap from the group of Greiner at MIT, and you can actually image. So they call it quantum gas microscope. So you can actually image the positions of these atoms, and you can see them fluctuating and so on. So it's really quite amazing experiments, okay? So, and again, you can see that, at the edge, the density becomes smaller. This is a two-dimensional picture, okay? And so we are interested in these edge properties here, okay? So just to recount, what we do is useful to start with a single particle first. So let me start with a single quantum mechanical particle, okay? So this is in a harmonic trap. So this is a quantum system, so I can solve the Schrodinger equation to get all the eigenvalues and eigenfunctions. And so what you see is that, I mean, this is because of the quantum fluctuations, it fluctuates. And so what are the eigen? So Schrodinger equation, we know all how to solve this Schrodinger equation. So the wave function is precisely a Gaussian times the Hermite polynomial, where this alpha here is just a length scale which is induced by the trap, which is square root of m omega by h bar. So it's the inverse of the width of the ground state wave packet. And the hkx are just Hermite polynomials. Okay? So these are just orthogonal polynomials. So one thing to notice is that even at k equal to 0, this is a pure Gaussian, because this is 1 and you have a pure Gaussian. So you still have fluctuation in the position of the particle. And this is because of the quantum fluctuations. There is no temperature. At 0 temperature, this particle is sitting in the ground state. But still the ground state energy is non-zero, and it's because of the quantum fluctuations. And of course, at higher temperature, it will have both quantum as well as thermal fluctuations. But okay, so let's just look at this. And so now I want to put n particles, okay? So not just one single particle, but I have n particles. And they are fermions, which means that I cannot put two fermions in the same level. Okay? So if I'm interested in the ground state energy, I have to just put the minimum I can do is to put them at the first n levels. I fill up each one level containing one particle, and the many-body ground state wave function you can write as because it has to be antisymmetric wave function, because this is a fermion. So which means that if you interchange any two coordinates, you will get a minus sign. In other words, when the two coordinates are equal, it should vanish. And the simplest way to achieve that is to write a determinant constructed out of the single particle wave functions up to the n level. And this is what is called the Slater determinant. And so what we have to compute is the Slater determinant, so ground state wave function, ground state many-body wave function, which encodes the quantum fluctuation of this n-body system. So it's just this determinant of the single particle wave functions. And this determinant is easy to calculate. So for instance, if I have just 2 by 2 okay, I'll have an example later. So what happens here is that when you put in this determinant, remember this is Gaussian times Hermite polynomial, the Gaussian factors just come out, and what you have is a determinant of Hermite polynomial. And determinant of any orthogonal polynomial, you can always write in this van der Monde form. Just to show you an example, let me just show you. So let's take the example n equal to 3. So here the Hermite polynomials are 1, 2 and 2x times 4x square minus 2. So if I want to compute this determinant, so you see this is just this determinant here. So first thing I can do is I can take out the factor 2 from the second row, okay, outside, and then I can just multiply this guy by 2 and add to this third row and take out a factor 4. So overall you will get a 8 times determinant of 1, 1, 1, x1, x2, x3, x1 square, x2 square, x3 square. But this is what is called the van der Monde determinant, and so for this van der Monde determinant you can actually compute the determinant explicitly, and it's just the product of these 3 factors here. And this generalizes to any n particle system, and so what you have is therefore just this van der Monde factor. And you see here, so this term comes purely because of the Pauli exclusion principle. This will be 0 when xj equal to xk. And so this is the wave function, quantum mechanical wave function. So if you take the mod square of that, absolute value square of that, so that is just, you can interpret it as a quantum probability density. So it's a measured probability density because it's positive and it's normalized to 1 due to this constant here. And so this is square of that. So this is just exponential minus xi square times xj minus xk whole square. So but you stare at it and you see immediately that this is exactly the joint distribution of the eigenvalues of a GUE random matrix. And there you remember in the GUE case, this van der Monde factor came just from the Jacobian of the transformation. It's a mathematical origin. But here you see it has a real physical origin. It's because they are fermions. I mean they are just and it just comes due to the Pauli exclusion principle. Okay. So therefore, so these are the 2 problems. So fermions ground state wave function square is exactly same as the joint distribution of the eigenvalues of the GUE matrix. And therefore, what you have is a one-to-one correspondence between the positions of the eigenvalues up to this factor alpha, up to some constant factor. This is exactly in law, they are exactly same as the eigenvalues of a GUE random matrix. Okay. Now, this identification actually helped us quite a lot that I'll talk in the last 5 minutes. I'll finish. And so essentially, I mean, so once you know that, then everything you can translate from the random matrix language to this fermion problem, and you can predict a lot of properties, in particular the edge properties. And so you see, first thing is that it should be a semicircular law, the average density of fermions, because the eigenvalues are semicircular law in the GUE problem. So you can ask, what about the position of the rightmost particle, okay, at 0 temperature? So again, position of the rightmost particle is exactly and it's a random variable which fluctuates because of quantum fluctuation. I want to know what is the statistics. So from this mapping, what you see, this is exactly the largest eigenvalue of a random matrix, and therefore the position of the rightmost fermion has, okay, again there is a deterministic part and there is a fluctuating part. This is slightly different from the GUE, because GUE I put n to the power minus 2/3. That's because I chose the variance to scale like 1 over n. But okay, it's just a trivial factor times this Tracy-Widom distribution. So this is the first prediction on this non-trivial prediction that you can make. And in fact, to me, it's a very nice physical system where Tracy-Widom distribution appears, which probably can be possible to measure experimentally, not yet. And so this is, as I said, is a sort of very nice physical relation of the Tracy-Widom distribution, apart from these growth models. And then the second question you can ask, what happens at finite temperature? Okay, so I'll be very brief here. So this is the 0 temperature, and the moment I introduce the temperature, the connection to GUE is lost. There is no random matrix correspondence anymore, and so we have to do something else. And again, so now I have to skip the results. I mean I'll just tell you the results. I won't give you the details. So what happens at finite temperature? Okay, so what is the problem at finite temperature? So finite temperature means that I can excite, I can take an excited state. For example, this was the ground state where I fill up to n-1 levels. So if you have a finite temperature, you can excite some of the fermions. So it can go into, the level, occupied levels can be these 2. There's a gap, and then there's these guys here. This can be one possible excited. So you have many possible excited states. Okay. So the excited states, so their total energy is just the sum of the occupied levels. So this K1, K2, K3, Kn are the occupied, denote the quantum numbers of the occupied levels. Okay, and then for each such state, many body state labeled by this K1, K2, K3, Kn, you calculate the Slater determinant square. So this is your probability density if you are in that particular excited state. And then you have to multiply this by the Boltzmann weight of that state, and temperature appears here. Okay, so this beta is not the Dyson index, it's a temperature, real temperature 1 over kBT. And then you have to normalize it. Okay, so this is your joint distribution of the particle position at finite temperature T. At 0 temperature, when beta goes to infinity, this reduces to the Slater determinant of the first n levels, and that was the GUE. But now you have a finite temperature, you cannot interpret this as a random matrix ensemble. And so this is the measure you have to work in, and you have to ask, given this temperature T, given this probability distribution of the n particle positions, what can I say about the rightmost particle? Okay. So I have to just, to calculate the probability distribution of the rightmost particle, I just have to take this measure here that I mentioned, and I have to integrate from minus infinity to W. So that's the problem that we looked at, and I'll just tell you the results without telling you any details of the calculations. So it turns out there is a natural characteristic temperature which is of order n to the power 1/3. What is this temperature scale? This is actually, if you look at the interparticle distance between at the edge, which you know how to compute, I showed you already. And if you, by just integrating the density of states and setting it to be order 1 over n, you can estimate this scale. And when you put this interparticle scale as comparable to the de Broglie wavelength, or thermal de Broglie wavelength, which is h bar over square root of temperature, so what this means is that if this interparticle distance is much bigger than the de Broglie wavelength, then you have a classical physics. Whereas if it is much less than the de Broglie wavelength, then you have a quantum physics. Okay? So this is a natural temperature scale which goes like n to the 1/3. And if you set your temperature to be order n to the power 1/3, and let's call it this parameter T here, I just fix a parameter T here. So I set T over h bar omega, which is dimensionless variable. I make it T. So T is just a parameter for me for the moment. Okay? So if I do that, and then if I analyze this distribution, what we were able to show is that the probability distribution of the rightmost particle position again has a cumulative distribution, again has the Fredholm determinant form. This S is probability that is less than or equal to S, and this Fredholm determinant with a kernel which is given exactly by this form. Okay, precisely this kernel. Okay, with z prime going to S to infinity. And when you stare at it, you immediately see that this is exactly the same kernel that appeared in the KPZ problem at finite time. You remember I showed you the result of the mathematicians and the physicists, that this was precisely the KPZ kernel that appears at finite t. So this parameter t, which in my case is a parameter, is precisely the time in the KPZ equation. Okay? So the finite temperature is like, so small temperature is like large time t. So when temperature goes to 0, like t goes to infinity, then you get the Tracy-Widom distribution. But when temperature is finite, then the time is finite, and you get this KPZ, finite time KPZ kernel. Okay, so this is the sort of main result that we have. So just to summarize, this is the relation to KPZ. So I told you, so I've already said that this is the KPZ kernel was precisely the exactly same kernel appear. So with this identification that the parameter t becomes the time in the KPZ problem. Okay, so this is the identification. Okay, so I'm almost done. So just to summarize, so therefore as a function of temperature, this is T over h bar omega. So there is this characteristic scale n to the power 1/3. When temperature is much smaller than the characteristic n to the 1/3 scale, it's like the quantum world wins. So then effectively the system is described by the 0 temperature picture, which is the Tracy-Widom distribution. If temperature is much bigger than n to the power 1/3, then it's a classical world. The quantum nature of the particles is not important. And then classically the particles, the fermions forget their Pauli exclusion principle. They are just independent Gaussian variables because they are in a harmonic trap. So they are just independent Gaussian variables, and therefore the distribution of the maximum is given by the Gumbel distribution. So Gumbel here, Tracy-Widom there. But if you are sitting exactly at that point, that is if you set temperature to be n to the power 1/3 by some parameter t, then here you have a whole family of distributions parameterized by t and given by the Fredholm determinant with this finite time KPZ kernel. Okay, so this provides a finite time generalization of the KPZ. I finished. Okay, so this is more details. So let me just summarize and conclude. So basically the Tracy-Widom distribution from random matrix theory is ubiquitous, as we have seen many times. And the height distribution in 1 plus 1 dimensional KPZ equation at late times is given by Tracy-Williams distribution. Free fermions in a 1D harmonic trap at 0 temperature provide a physical realization of the GUE eigenvalues, and also the H physics in 1D cold fermions at finite temperature is KPZ at finite time t with this identification. Okay, so I hope I've just shown you that these 3 different problems, they're actually all connected to each other in a sort of rather intricate way. So thank you very much for your attention.